How can the Lean Six Sigma body of knowledge be applied to a real project? Here's a simple example illustrating the Lean Six Sigma project cycle from start to finish. It is informed by countless projects submitted here at SSGI over the years. To structure the project, we follow the DMAIC framework. It includes 5 phases: define, measure, improve, analyze, and control. First, we turn to the define phase. The problem statement. The Evercool company manufactures and distributes commercial air conditioning units, as well as provides existing customers with replacement parts for units in need of repair. Customers have increasingly complained that the time to receive these parts is long. Several have gone weeks without them. A Lean Six Sigma project has been approved at Evercool to study this problem and determine how the order fulfillment cycle for replacement parts can be shortened. The project goal is to reduce the time from customer orders to delivery by 30%. A project charter is a statement of a project's goals, scope, timeline, and participants. The Evercool goal just expressed is a 30% improvement in the fulfillment cycle. The charter also expresses scope, what needs to be done and what does not. For example, the order cycle for new air conditioners will not be addressed. The timeline is 3 months. Finally, an interdisciplinary team of 3 staff has been assigned to the project. Next is the measure phase. SIPOC diagram. We begin with a SIPOC diagram shown below. It helps us identify all suppliers, inputs, process steps, outputs, and customers before proceeding with the project. Further, it assures that no variables have been left ignored. Cost of poor quality. The cost of poor quality, COPQ, defines the economic consequences of failing to meet process goals or customer expectations. In this example, COPQ can be measured in part by estimating the costs associated with failing to fulfill orders within a reasonable period. Indeed, poor quality almost always incurs costs. They can be traced internally to the organization, such as scrap and rework, or they can be traced externally, such as customers taking their business elsewhere. Benefits and costs. Projects need to justify themselves by delivering benefits in excess of their cost. Here is how we could estimate the benefits of this project. The marketing department estimates that Evercool loses an average of 3 customers every month due to poor service. These accounts average $40,000 per year. So COPQ is 3 times 12 times 40,000, or 1,440,000 in lost revenue per year. The finance department, on the other hand, estimates that this represents a loss of about 200,000 in profits per year. By shortening the cycle, it has been estimated that at least half of this amount could be saved, or $100,000 per year. 3 staff will be assigned part-time to the project for 3 months at a cost of $50,000. In addition, the cost of IT changes have been estimated to be $40,000. Comparing the benefit of $100,000 with the cost of $90,000, the benefits in 1 year exceed the cost. Data collection. Data collection is an important part of the measurement phase. Since fulfillment time is the primary focus, collecting data on the length of time between placing and filling an order needs to be collected. The table below summarizes average lead times over a 15-week period. For example, the average lead time for week 1 is 8 days and week 2 is 11 days. Bar charts. Bar charts are very helpful in uncovering the root cause of a problem. Here is how one can prove useful in the Evercool project. First, the possible categories that can explain the delays are identified, and then frequency data is collected for each. These categories start with supplier-related issues and end with transportation issues from suppliers. The second column shows the frequency with which these categories have been observed over a 1-month period. Finally, a bar chart is constructed. As you can see, each bar represents a category, and the height of the bar represents the frequency associated with that category. Also notice that the bars have been ordered with the highest frequency on the left and the lowest on the right. This is called an ordered bar chart. Process mapping. But data is not enough. It also is important to understand the flow of steps between receipt and shipment of the order. To do this, a value stream map, or VSM, is created. Next is the analyze phase. Root cause analysis. In root cause analysis, we attempt to determine the real cause of a problem. So we try to move past a simple explanation that might focus only on symptoms. As you can imagine, solving the symptom is unlikely to have a meaningful or long-lasting result. 2 tools are helpful in root cause analysis: Pareto charts and fishbone or Ishikawa diagrams. Here we will focus on a Pareto chart. A Pareto chart is a variation of the histogram. In addition to identifying the magnitude of the problem, or in this situation, the frequency associated with each category, the Pareto chart also displays the cumulative contribution associated with solving more than one problem. So the Pareto chart might indicate that by addressing the top 3 problems, 83% of the total problem may be resolved. Here is how we can interpret the right-hand vertical axis. If supplier-related issues can be resolved, about 40% of the fulfillment delay can be addressed, and about 65% of the delay can be addressed if supplier-related and quality issues are resolved. Gemba Walk. A Gemba Walk is a workplace walkthrough whose objective is to observe processes, employees, trouble spots, and bottlenecks. They become candidates for process improvement. So this walk is another strategy for uncovering process inefficiencies and observing the possible reasons behind these delays. In this example, the Evercool team would walk through the entire fulfillment process, thereby gaining first-hand knowledge that could be instrumental in continuing to make sense of the data that has been collected. Process capability. The concept of process capability compares what the customer expects to the capabilities of the process. If the process easily meets customer expectations, its capability is high, while if it is incapable of meeting them, it is low. When we start a Lean Six Sigma project, process capability is usually low, but after the process has been analyzed and improved, it should be higher. So process capability can be used both at the early stages of a project to underscore the need for process improvement, and again at the end to confirm that the efforts made have been successful. In Six Sigma, there is a formal way to express process capability. Process capability, CP, measures how close a process is running to its specification limits relative to its natural variability. These specification limits reflect customer expectations, which are compared to the natural variability associated with delivering customer results. The larger the value of CP, the less likely process output will fail to meet customer expectations, called upper and lower specification limits. At the end of the Evercool project and after sufficient data has been collected, we would expect CP to be larger than 1. 5 whys. Repeatedly asking why can help uncover the layers that can lead to a better understanding of the problem. It is another step in getting to the root of the problem. In Lean Six Sigma, it is tradition to ask 5 why questions, and each probing deeper to find the real or root cause of the problem. Here are 5 questions that can be asked in the Evercool project. Why is there a delay in the fulfillment process? Why are orders taking so long to process? Why are there backlogs? Why are we unable to clear backlogs? Why is there no procedure to deal with these delays? Data analysis. Data is important, but raw data is not enough. It needs to be analyzed in a systematic way, which often requires the use of statistics. So we might, for example, compute the average fulfillment times reported previously. That average is 8.67 days. It represents the central tendency of the data. We can also use more advanced statistical analysis, such as regression correlation or hypothesis testing, to learn more about the data. Data is also critical for comparing old and new ways. It avoids ambiguous comparisons, such as, the improvement process does seem to be working, or the fulfillment process is a bit faster. Indeed, when data is used, we can be more explicit. The fulfillment process has improved by 12%. Analyzing other data. However, the analysis phase is not limited to the use of statistics. It also involves analyzing value stream maps, the knowledge gained from Gemba walks, answers to the 5 whys, or data displayed in a Pareto chart. It all helps when analyzing a problem and learning as much as possible about it. Improve phase. Next, we turn to the improve phase. Eliminate non-value added steps. Armed with the insight gained during the analysis phase, the next step is improvement. Non-value added steps are eliminated to the extent possible. Delays, errors, and waste are addressed. Even value-added steps are explored to determine if they could be made more efficient. Fumiya and Poka-yoke. One way to address many of these alternatives is to schedule a brainstorming session attended by relevant stakeholders, during which time all of these possibilities for improvement are discussed. Their input can be instrumental in motivating change and limiting resistance that often interferes with what has to be done. During the brainstorming session, it might be useful to rely on FMEA and Poka-yoke. Failure mode and effects analysis, FMEA, involves the staff anticipating problems before any changes are implemented and then taking steps to avoid these problems. In Poka-yoke, staff consider ways to prevent future errors. Pilot testing. Pilot testing can also be used during the improve phase. It can make sense to implement small-scale improvements and then use the results to prepare for the implementation of the full-scale version. Resistance to change. The improvement stage is often accompanied by training. It familiarizes those affected by the change to the new ways. At this point, resistance from those affected by the change often emerges. As a result, it helps when the team has some familiarity with the concepts of change management. Nonetheless, they must at least be sensitive to the reluctance of those affected by the change to adapt to new methods and procedures. Comparing old and new. Has the project been successful? At this point, it is important to compare the new system with the old. In our example, the average time between order placement and delivery was reduced from 8.67 days to 6 days. This is clearly an improvement that has exceeded project goals. Yes, it has been successful. A more formal and more convincing way of comparing the two is hypothesis testing. This statistical test determines if there is a significant difference between the two approaches or if the differences can be attributed to the inherent variability that occurs in all processes. Control phase. Finally, we have the control phase. Outputs change over time, so establishing a monitoring and control system to ensure that this does not happen is a critically important step in a Lean Six Sigma project. Indeed, any project that fails to create a monitoring and control system is a project that has not yet been finished. Control charts are at the center of the monitoring and control function. While the statistics behind these charts can be quite complex, the basic concept is simple. Samples are periodically taken from a process. The sample mean is plotted on a chart, and as long as they remain within specific boundaries, the process is considered to be in control. In constructing the control chart, we use the long-term average output as the target. The upper boundary is called the upper control limit, and the lower boundary is the lower control limit. Here is a control chart for the Evercool case. Notice that the sample means in this example are within the upper and lower control limits, so the process can be considered under control. While this example required a simple X-bar chart, because we were monitoring process means, other charts might also be used. For example, a P chart would be used if we were monitoring process percentages, such as the percentage of customers who complain about customer service. Control plan. A control plan goes one step beyond the control chart. It takes the 30,000-foot view and focuses on managing the entire quality control process. As such, it goes beyond establishing quality control charts. It identifies the process owners responsible for the process, as well as the corrective actions that should be taken when an out-of-control signal is observed. The outcome is a formal control plan. That's it. This is a very brief introduction to the way we would organize and manage a Lean Six Sigma project. While your project may involve other tools and is likely to go into greater statistical depth, the basic format and direction described here can guide almost any Lean Six Sigma project. To recap the basic issues of a Lean Six Sigma study, follow a framework, clearly define the problem, measure the problem parameters by collecting data, analyze the data with such tools as Pareto charts and value stream maps, improve the problem, and control the process such that it continues to meet goals. For a full range of courses, from Yellow to Master Black Belt, as well as courses that focus on operational excellence, management, and leadership, visit us at SixSigmaGlobalInstitute.com. Thanks for watching.